first we discuss the background of why we established the quantum mechanics, the failures of the classical, right? Classical mechanics, and then we have the origin of quantum mechanics. That is chapter 1 we are going to cover today. I hope if not finished, we can continue. Then we are going to establish quantum mechanics. How to establish quantum mechanics, we need the math tool. Math tools. That is chapter 2. Okay, so now here, this is chapter 1. This is chapter 2. And those, for example, we introduced Dirac notation to describe the quantum states. We introduce operator, and then we have a lot of different type of operator. For operator, some operator has eigenvalues, eigenstates, right? So those are the tools we prepare. And with these tools, we are going to establish quantum mechanics with a theory, which is of quantum mechanics, which is chapter 3. We have a postulate, concept, and postulate. Postulates. All right. So when have I read this, we are going to apply. I think I have space. Okay. So apply. Application first. They go to 1D. 1D problems. That is chapter 4. Okay. And 1D problem is a single particle, right? So potential will, then we only consider single particle. So that is a single particle. Different type of potential. You will see that in here we establish Schrödinger equation, and the key to characterize, or each system has its specific property because of potential, right? So then when we have this one, so we are going to go to angular momentum. Because we know when we go to the high dimension problem, we have angular momentum. That is chapter 5. The angular momentum we are going to discuss, orbital angular momentum and spin introduced. Then we go to 3D. 3D problems. Okay, so this is chapter 6. Again, we still consider single particle. First, those application actually is first a concept, and then we are going to learn how to deal with or solve each system with quantum, Schrödinger equation with the mathematical tool. Once we figure those, then we can go to many particle system, right? So, rotation. After this, we are going to introduce rotation and addition. Now we are going to prepare for consider many particle and addition. Okay. Of angular momentum. Because now we are prepared to try to consider one part, 2 particles, 3 particles, so many particles. Then if you consider 3 dimensions, so each one associates with angular momentum or the general angular momentum or orbital or spin, right? So those like here, that for single, now we are going to consider in general format. Then we go to identical particles. That is many particle, right? Many particle. Now we extend to many particle system. For many particle system, you will see how to deal with this complicated. Not only because single particle only have a potential, external potential, but the many particle, in addition to the external, we have interaction. So how to deal with those? And then in addition, we also have the symmetry. Single particle symmetry like ADG concern or the rotation symmetry correspond to the angular momentum. But in here, we have also exchange. Because many particles, if they are identical, follow the chain, you will see that some of them follow the Fermi's, some of the bosons, right? That is the topic of the chapter. So that is chapter 8, I think. Yes, chapter 8, chapter 7. That will go to next semester. Then after this, we are going to have the, so far here, this is a 1 dimension and 3 dimension. We all deal with the potential such that we can solve exactly. We can get analytical solutions. But in practical, we know very complicated, even for single particle with potential complicated, we cannot do so, we need approximation, right? So now we go to the approximation. Now we are going to have the approximation scheme or methods for time independent, okay, of, let's see, time independent. So that is independent potential, right? Okay. Potential. Or perturbation, right? Perturbation. That is chapter 9. Then time dependent. I think here I missed the time dependent. That is chapter 10. And since time limit, we may not cover all the subtopics in the chapter, then this the final is scattering theory. Scattering theory is, in most cases, they consider the potential is attractive. So the state are bounded states, so they have energy levels. But now, if we consider this unbounded, so like we have initial kinetic energy, then particle come to the target, it will scatter, right? So that is scattering theory. If we have time, I hope we can go through this. And here we also try to see the time. I think we just give a both basic like a Born approximation, and if we have done like partial wave approximation. So those are the framework for these 2 semesters, and I think this is a semester. Hopefully, all part of this is the part 2, and the major part, that part 1, right? That is this semester. Okay, now, can I erase this part? All right. Now, let's try to, how to say, suppose we are now 100 or 200 years ago, then we try to describe the dynamic nature of this, the natural phenomenal system in the physical world. How do we do that? Assume we do not have no any idea about the Newton's mechanics, about quantum mechanics. We just, as a human being, we look a lot of phenomena. Then we need to try to understand what is the underlying physics, right? So let's check. This is just a critical thinking. I think you probably you know that. So now let's think about this dynamic. First one, how to describe the dynamics of nature of physics, physical world. We not consider the chemical, and we just interested in this. Right. So first we need to observe, right? We just look at this phenomenon, then we are going to summarize. So first we are going to summarize summarize all the knowledge of the phenomena, natural phenomena. That is we need to. We first know, right? We need to know what happened, what kind of knowledge we can get. So that is observation, right? First, we need observation. Then when we have observation, we got a lot of the phenomena, and then we are going to summarize to see what is the inside or underlying physics. So with this, can you read this part, right? Okay. Then with this, what we are going to do, we are going to establish theory, right? Okay, so we establish a certain laws. Like Newton's law. Newton's law, because he tried to observe or see this the apple. That's one example, right? So, but then he several times, 1,000 times, he found, okay, there's a relation between force and acceleration. Then he said this law, second law, right? And also fourth law, third law. So that was the second, but then that is theory, right? That is the theory we establish by these laws and this concept. The theory includes this includes concepts and prediction. With the established laws, then for very simple case, second law, which we know if we can analyze force, we can predict what is the acceleration of the system and what is the trajectory of the part of motion, right? So that is this, and then that is theory. In this theory, we are going to see validity, right? Check or validity. I just check or validity. We are going to use experiment. First, we observe and we establish theory. Then with this theory, let's see whether it is predictable. If predictable, that means after the experiment validity, yes, right? So if not, then we have to back to correct which concept is not established, not correct. So we have to try to improve, right? So that is how this theory established. Yes. Okay. Let's just consider no. Just come back. Now, with the time passed, so as time passed, what will happen? We will see some of these new phenomena. That means the domain of our observation initially, if you consider it a macroscopic ball or the scale, now suppose we develop this instrument, increase the accuracy of measurement, then we found new phenomena, right? So that is when the time develops, so then the technique also develops, and then we have this one is enlarge the domain of the observation, or improve the accuracy of measurement. What happened with this? So we have we found a new phenomenon. Okay, so with the new phenomenon now, what we are going to do? We are going to see. Okay, still use a theory, right? So now we are going to use theory, which exists. This one, right? Okay, maybe it just come to here. So now, for the old phenomenon, for the first step, we found, okay, we established theory that works very well. However, with the time pass, we found, okay, by improve this accuracy of the measurement or open our mind and then with the world, what we found is we have some new phenomena. Then we are going to see in this theory. Okay. What do we say? Validity. I'm going to test theory validity or not. Okay. If yes, okay, then good. But in most cases, no, right? Then it challenges this one. So what we have to do? We need new theory. And that is what happened from this classical mechanics to the quantum mechanics. That is the, if we discuss the dynamics of nature of the physical world, that is, we know the first step establishes the classical mechanics, then down to here we will have this quantum mechanics, right? So now that is the basic development of this the theory here. Now, if we have need theory, the new theory, right? So now, if I'm going to say old, so now how from the old to transfer to the new one? Because it cannot be independent. If it's separate, then that means your new story, a new theory does not work on this one. That is not new theory, right? Just be covered. So what this means? The second one is how to transform or transit from the old theory to the new theory. That is, we need to consider the next step when we reach to here. Right, so now if I use graphically, consider this nature of world or the domain. I'm going to use Dn is Newton, but within the domain we have an old domain, Do. So Dn, if we consider that is domain of the phenomena which you observed, is correlated by new theory. So you can see here, you can see here, this series we cover O, right? Then if we define DO is domain of the phenomena is correlated by the old theory. Okay. Then what we see the relation between here. So now for this for the old one, the both new theory and old theory works. If only old theory works, new theory doesn't work, that is not new theory, right? So we require for this one, even though described by old, but both new and old that is must be. And of course, by convening old enough, right? So that is the for this the old domain. Then for the new, okay, for the new one, old doesn't work. Does not work. That is what happened. That is the relation between these two. Now, okay. So what we are going to transfer is from the old to new. We need to follow this, right? So we need to have this follow this or the relation. Now let's try to remind you, which actually we are going to discuss in more details in this 605, this electrical mechanics from Tuesday and Thursday. But just remind, right? So then we want to know what is this old theory, and then what is the difference between old and new, and what we need to establish new, right? So just try to remember.
Oh, that means both new and old theory work.
Yes.
It's in the previous domain.
In previous domain, new should be also works on the old one, but the new domain, old work doesn't work. Old theory doesn't work, right? So, but why? I mean, later we are going to see that the new theory will have a kind of a limitation when you see this the quantum number which or the variable is bigger than the h bar or h, the Planck's not constant, then that's classical works. Even though the new theory also works, but old one is not, so we do not use new one. But new one should be explained. Okay, so now brief review this theory, right? Okay, let's see this in old one, right? And then we go to the, let's see the difference. So briefly, you know that we want to describe the status of system. How to describe the system, status of system in the classical mechanics. Let's just consider, okay, let me just even consider M particle, right? Position, at any time, what's the position? The series will tell us, right? And also, of course, acceleration, velocity and acceleration, all this information to give us status of system. M particle at t vertex, what is the speed, or velocity, what is the acceleration, right? So that is a discrete static. Second one, the physical quantity. Let me take this. In the classical mechanics, we have the energy, right? Each particle has its energy at time t, and the momentum, like linear momentum, or angular momentum, that is all vector, right? And other like potential or kinetic energy. So those are the physical quantity. Once we know this by the theory, right, we can solve those, we can answer those questions. So that gives it the physical properties. Then the theory, that is the theory, that is classical mechanics. If you remember, we have either Newtonic theory that we are going to discuss at the beginning, introduce this theoretical mechanics. We are going to try to review what is Newtonian mechanics or analytical mechanics, right? So let's just give you mechanics and analytical. Newtonian, we use R and the linear momentum to characterize each particle, and then for n-particle system. So that is a state, right? The state of system. But in analytical, we introduce a generalized coordinates and general velocity. So we're going to use Q, and it's a G. Why is G, not I? Later when we go to that class, you will know the details. And then the general velocity, Q dot. Or in this Hamilton and this phase, we use general coordinates and the general momentum, which is the conjugate momentum of general coordinates. So that is different way, different than the mechanics we are used is different. And then this equation of motion. We use second law, right, in the Newtonian mechanics. So net force on each particle is, suppose the mass does not depend on time, so we just consider m, and the change of momentum, right? Each particle, dt, I from 1 to n. Okay, so the net force on each particle actually include the external and internal. The external rise particle plus internal, if I have a j not equal to I, so F ji, external and internal. Then this is to get force. We can also have this torque that is correspond to the angular momentum. This is a linear momentum, and for S particle, the net torque is follow this derived from this Newton's second law. We have angular momentum dt, right? And angular momentum is the product, a cross product of this r with the linear momentum. But in the analytical mechanics, we are going to introduce Lagrange equation, right? So that equation wasn't described by in this analytical mechanics. So we are going to use this Lagrange equation. That is famous. I think you may also know this. Equal to 0 if a force is Fi conservative force, or general force if Fi is non-conservative. Those part is physics 602. We are going to go to detail and will not give too much. But then the energy, for example, energy, to describe energy system, it is kinetic energy plus potential energy. Here the same, but here it is a function of, okay, it is a sum of all the kinetic energy, which is Ri dot square plus potential energy, which is a function of Ri. Usually, maybe some of them depend on this velocity that is like electron field. So this analytical mechanics energy, kinetic energy is a function of general coordinates, generalized velocity, qg dot, and t and plus potential also is a function of general coordinates and maybe general velocity and t. Now the last one is some conservation. Conservation theory, right? Or laws, conservations, we have energy conserved. So a lot of so if this net force equal to 0, then we have a linear momentum, right? Is constant. Or if the net torque is 0, so this angular momentum is constant. If the force is net force, all are conservative. Okay, I use symbol means conservative. Then we have energy is conserved, right? Those are the basic, the classical mechanics. Similar here. Similar in this case, okay, I will not say same. Because this conservation of whatever the analytical and mechanics or Newtonian mechanics is the same, because this is a theory. This is the properties will not change by introduce different variables, right? So that has to be same. But usually we will use this one. Okay, like Hamiltonian is let's just do it here. I don't want to spend too much time. The details, since we are going to discuss lots of details. But the key here is the feature. Okay. So the basic feature of those properties, feature of state. In classical mechanics. Okay, all are determinate. Native and continuous. That means we can measure exactly to determine at time t vertex what is velocity, what is acceleration. That classical can give us by solve this either the Newtonian equation or the analytical, we can solve exactly, so we can determine any exact position or momentum. And those variables are continuous, not discrete, right? So there's no any difference, any other features. So those are described by the classical mechanics. But as I say, as time passed, but we increase our accuracy of measurement, and also we broaden the observation, but we found some new phenomena. Those new phenomena was the whole theory cannot explain, so that the failures, now we are going to discuss. What happened? Failures of classical mechanics in when the time is end of 19th century and early 20th centuries, right? That is what happened. And so now that is here we enlarge, just remind you, enlarge the observation domain. That is, now we go to D-N-Bridge microscopic. Yes, microscopic scale or word. And in this word, because of course we have to design the more accurate measurement, so you can find a new phenomena. That is in this word. And what fun? The old theory cannot explain or failed in this work. That is in the domain FDN, right? New domain. So, okay. Now let's do some of example. What kind of failure? We just select some of the typical examples and see what failures and what to. Those failures bring some question, and then how to solve this question. We establish or to introduce a new concept, a new method, and new ideas. That is established quantum mechanics, right? So examples. Okay, now before that, we first give some idea. The first one, the failures. First one gave us A. The first one is a particle aspect of radiation. Okay. So we know the radiation is a wave behavior, right? How to, or we found out the wave behavior, but it has this particle behavior or particle aspect. That is, we found the new phenomenon, and which failures cannot be explained by this old theory. So then we first, what is a particle? When we see particle aspect or particles, when we describe particles, we need, okay, or described by the particle variables like position and momentum, linear momentum, and some other, maybe energy That is described by particle noodles. And then they characterize, take localized, right? It is localized because we can exactly find, let's say here, this, here, right? Determinant. We can determine exact vertex. So that is localized behavior. It is a particle. We know when, the time, vertex. Here, there's a particle behavior. It is not a wave behavior. Wave behavior is spread in the whole space. So I can describe this as a particle behavior, right? Okay. So that is, but how about wave? Wave we describe by what? Describe wave by wave function, right? So that's usually we use psi, which has a position, r, and time. So that means the wave is spread in the whole space, but this one will give us amplitude of the wave oscillation and then phase factor. Alright, here we have k, you know k is a wave number dot r, and minus omega is a frequency, right? So that is a phase, totally characterized by this, and you can see that's totally different, right? So this is the r, it's totally localized to each individual position and individual properties. But here, this is just a wave function. That's a function to be characterized to be spread in whole space, right? Totally different, opposite this particle behavior. Characterize, takes is delocalized. Delocalized in the whole space. So that is totally different. Then the question comes back to here. If a wave is delocalized, extend, or defined in the whole space, how can that wave behave as particle? But we do find this behavior. So now let's do one example here. You know K, right? So I do not need, okay, so K and the relation between, okay, I think that's we cannot go to this. Now let's go to examples. See what kind of aspect, the particle aspect we have. And that is very strange, cannot be explained by the classical mechanics. Since classical mechanics, particle is particle, wave is wave. They are well separate. Example 1. Okay. Example 1 is black radiation. A black body radiation. You know the black body radiation, right? The black body means all this light coming to this black body, it will be 100% observed inside, right? And then what happened? Because it absorbed the energy over the radiation and then it will emit inside, right? So inside the body. That is phenomenal. But this is a wave, right? Because it is radiation. So there must be wave behavior. Now let's see what happened. Okay. So now this black body, we have this the total power. I follow this equation here. It's a famous equation. This is a Stephen Boltzmann, right? Follow this law. And here this coefficient A, and this is called A shape. A equal to 1 for black body. It's the biggest the radiation, and A smaller than 1 in general, right? That means not 100%. So when A okay, sorry, equal to 1, not 0. And sigma is a constant. So sigma This gives us 5.67 multiplied into -8 volts meter square per Kelvin. This is as to symbolize, or as Stephen Boltzmann. Constant. Then you can see the total is the total power. Proportional to temperature to the force power, right? Okay, in order to get this result, we need to know the energy density distribution for given frequency, because the radiation has a frequency and also has the temperature. So to obtain this one, we need this one. That is okay, energy intensity, energy density, sorry, density distribution function, distribution. Now this one gives us a question or challenge. So now let's give you the measurement of the experiment. That is this one, right? So as a function of frequency. Okay, so the curve is like this. For given temperature, okay. Now, try to explain this. What we found is, now, I'm going to use color. To obtain this is observed, right? So now, what we observe. Now we are going to see why they behave like this. So we need to interpret it in terms of wave behavior. Because it's wave, right? So in terms of this, the first one is at a theory, right? Let me see theory. That is observation. And then we are going to see theory at a high frequency. At high frequency, it is follow this. Okay, let's obey. Obeys Planck's law. Okay, the law is like this. This, the energy density. Oh, sorry, this is temperature. Is proportional to this Q of this frequency, and the temperature is exponential. Beta mu over T. So what does it look like? High, right? This is a higher, so now this is like this. That is, okay, just see. It doesn't work because you can't divert when the frequency go below, but very high they follow this. That means after this, it explains this what happened here. So that means the series cannot cover whole. Then now, how about the low frequency? This is 1, 2 at low frequency. This is obey, or we can find this obeys this really James law. This law gives us this. The energy density is followed by definition is the number of how much the moles of this forgiving this frequency and the energy average. And here, the energy average is, okay, let me give it first, formula 8 pi mu2 square C over Q and average. So that means it is proportional to the Q, the square of the mu, but we have this one. This is the average of energy. Then how to obtain this one? This. Since this is this wave behavior, we are going to do the average of energy, use this distribution, Boltzmann-Maxwell distribution. So that we follow the statistic, we increase integral from 0 to the infinite of this energy, and for energy, given energy, with the distribution is Boltzmann dE. And divided by normalized, right? So normalized. That is just follow, and you see this is continuum. Because this is classical, right? So the energy be continuous, so we can do the integral. Then follow this result, very simple, this will be about Kt. K is what's my constant, right? So now, then you put here, so with this, because this so with the low frequency, it is equal to, let's just substitute here, 8 pi mu square over Q, and then Kt. Now you can see this is proportional to T by the square, not Q. So what happened is, I could use the same color. So here, the low, that is low frequency, also follow only when the smaller case, but for the finite intermediate step, you can see both are diverse. That is the figure. So now this is G. Unfortunately, if we use the wave behavior of this radiation, we apply this, ENM, the classical, so now this area. Classical physics, because here this is this is not only mechanical, this includes statistic analysis and also the ENM, right? So those details. So here, that is what happened. Then how to solve this? This is by this Planck, right? So Planck, you have to remember him, and he made the contribution. Planck's energy density distribution. He make assumption. Without this assumption, he cannot go further, right? So his assumption, or postulate, energy E is quantized. What that means quantized here. We assume this is continuous, but he said no, it is not continuous. It's quantized. If you quantize, what happened? You will see you can successfully expand the whole range of the frequency of this distribution. Very successful. Then we are able to come back. Why this is successful, right? So that is the now quantize. What the quantize means energy. Okay, for energy for giving frequency is very simple. So n can be 0, 1, all are integer number, right? That is the quantize means. And then this one is for each single particle energy, and we know this particle is a photon, right? But later we are going to give a discuss. However, we know that means quantize means you cannot continue because this is always this number, discrete number with this. And here introduce the Planck constant. He used that, so that is very important constant. We know that is to characterize the quantum behavior, right? Constant. Very simple. Once we have this idea, and then we go back to calculate this again. Okay, he used this idea. This is a normally statistic, right? So this is good, but the only difference here, we are going to deal with the energy as a quantized. So then for the quantized statistic, it's not integral but summary, right? So now that is different here. Sum over O. Now this n here from 0, so now the n from 0 to infinite, all the integer number. Then the energy here, right? So this energy is NH mu. And each one still follow this distribution, so the exponential minus, now the E is declared NH mu over KT. Okay. That is the numerator, and denominator is just normalized, so we have this. Then this formula is not simply KD, but you will see it's, later you know that is Born-Einstein distribution for the pronouns. But here we just have this formula, and then later we're going to come back to see this formula, what this means, right, in next stream. So that we have. Okay, so once we have this, then we come back to here. So this distribution is the formula 8 pi mu square over q, c to the q. But here h mu over exponential h mu over kt minus 1. This one, I'm going to use red color, exactly is correct. Model or theory. Let's use oh, I think time is already here, right? Okay. You have another class, right? No. Okay, can I just use 1 minute, 2 minutes? Okay. So we have finished here. Now, when we here, so we have this formula, but you say, okay, if you numerically, you can just use that formula, you use a math lab, whatever, you can plug this. Now, can we cover, because these two series works either high friction and low friction, and you will see with that formula, when we go to mu, go to high or low, this go back to this. So that means new theory covered all theory, right? That is that one. So now you can see here, let's say for this low mu, you will see the low, we do the Taylor expression, right? So this one is 1 plus this one, and 1 cancel, right? So the low is very easily, you can see, okay, approximately, that is, this one is still Q here, and this H mu here, and go to H mu, and then this inside is, well, I just gave you the details, and you will see that is same thing. So that's equal to, and KT, right? That is this one. Then for the high mu, now high, that means this one is much, much bigger than this one, so we can remove e, minus 1, right? So then we go to the numerator, and you can see that is exact. Then you give this one Q, so that is H mu here, and multiply the exponential minus H mu over KT, and that is here. That is this one to the Q, to the mu to the Q, right? To the, so here you see this square is, so that is some constant to the Q, right? And then exponential. So you see this exponential here. Beta, did I? Beta mu. Okay, I think this be not just beta mu, because beta is KT, right? So you see this is beta, right? So that is beta minus beta. But we have a constant here. The mu. Here there's no edge here. Oh, H bar, yeah, beta. Beta is let me think about that. I think some, yeah. But at least you know now, we can cover all. And the key is very simple, just here. Okay, this is a particle behavior, right? Particle aspect. So that means the wave has to aspect a particle aspect, then we can expand very well. So that means this radiation actually duality either behave like particle or wave. When it became behave like particle, when behave like a wave, we are going to discuss later, right? Okay, so Wednesday we are going to the Adam's rule. Okay. Tomorrow is still here. I think we have another 2 new students and they do not know their case, so I'm going to still use this room. Then we will move to Adam's rule. All right. It's over.
Hey, what's up, everyone?
Hi.
How are you, Dr.
You just take a rest on your life.
Yeah, pretty much.
Good.
What's everyone's names? Nabi, yeah, I remember. I met you the first day you came. Did you get everything sorted out with your housing?
Yeah.
That's good. What's your name?
No.
You? I'm Zane.
Can I use this now?